Oh, I forgot to uh,
Right.
turn that on, actually. Hold on. Should be on. Let's see.
Yeah, it's on. Right.
So, welcome everyone to Climate Chat. I'm your host, Dan Miller. And today we have our very special returning guest, Leon Simons. And we're going to be talking about James Hansen's newest paper titled Global Warming Has Accelerated. Are the United Nations and the public well informed? That's the second part of it, of the title. And thanks, Stacy, for sharing the screen there. And so we have a lot to cover because the paper, to be honest with you, is 39 pages long. However, one thing you should know about it is that it's actually written in English. And by that I mean it's written in English that regular people can understand rather than all the scientific gobbledygook. It was like they really went out of their way to do this. And one example I remember, it said something about 40 GT slash Y, which anyone scientifically knows that's gigatons per year. But then it says parentheses, gigaton hyphen GT, billions of tons. So it actually explained that example of the units, and it really uses regular words. So I suggest that you try to give it a shot and then maybe read through at least the abstract. And a link to the paper is in the video description. Anyway, we have with us Leon Simons. Leon Simons is a climate scientist out of the Netherlands, and he's the executive director of the Club of Rome of the Netherlands, or you head that up. And he also was a co-author with James Hansen on the paper from about a year and a half ago, Global Warming in the Pipeline, which was another breakthrough paper. In fact, this paper sort of builds on that paper. And also in this paper, while Leon's not a co-author, he did get a special acknowledgement with his own paragraph in there thanking him for his contributions that made this paper possible as well. So, Leon, it's great to have you here. And it's great that you'll be able to walk us through some of the science that's in this paper. But before we do that, I'm going to go through at a very high level, and I think a very understandable level, what are the key points of the paper. I'm not going to try to explain the science. Leon's going to go into that. This is going to be more of the what of the paper, not of the why or the how. But these are, if you kind of don't know anything else, these are the things that you should know. So I guess the first question are the United Nations and the public well informed about accelerated global warming? And the answer to that is no, obviously. I mean, that's why this paper was written. But then you might say, okay, what are the key things that the United Nations and the public are not aware of about accelerated global warming that they should be? And so the first one is that global warming has accelerated more than expected in the past 2 years, due in large part to the reduction of ship pollution. And that ship pollution is called aerosols. And we're going to be talking a lot about aerosols today. And this reduction came about because of new regulations by the International Maritime Organization, also known as the IMO. And they said, well, because of the health impacts of this pollution, it harms people, and we can talk more about that later. We're going to require ships to use cleaner burning fuel, and that with less sulfur in it by a lot, like 80% less, starting in 2020. It started in 2015, but the big rules kicked in 2020. So that happened. Okay. And that caused accelerated warming. And Leon's going to tell us why in a little while, but just for now, just believe that it did. Second, this inadvertent experiment, because changing these shipping regulations were sort of an experiment that we could take a look at, helped us understand that the impact of aerosols in cooling the planet is larger than the United Nations climate organizations like the IPCC had assumed, especially when these reflective aerosols are released over the pristine dark blue oceans. Talk more about that later. Third, because cooling from aerosols is more than we thought, and because of several other lines of evidence, the paper concludes that the future warming from CO2 will be significantly more than what the United Nations and the public believe. And fourth, and this is pretty important, because of accelerated warming, we are closer to what Hansen calls points of no return from and we're closer to those points of no return than the public is aware of. These points of no return include the disintegration of the West Antarctic ice sheet and the possible shutdown of the critical Atlantic and Southern Ocean currents. The Atlantic one being called the Atlantic Meridional Overturning Circulation, or AMOC, and people who watch the show are quite familiar with the AMOC. But this also includes the Southern Ocean going around the Antarctica. So either of those things, the collapse of the West Antarctic ice sheet or the collapse of those ocean currents, which would accelerate melting of Antarctica, both of those could lead to several meters, which for Americans translates to more than 10 feet of sea level rise in the next 50 to 150 years. And that would submerge many of the world's coastal cities and island nations that obviously cause havoc everywhere. Now, the shutdown of AMOC also causes lots of other problems besides that, including drop in rainfall across all of northern hemisphere, and therefore impacting agriculture everywhere, and collapse of the Amazon, and change of monsoons, and a lot of other things. So we're talking about really serious impacts here. And besides being closer to points of no return, accelerated warming also means bigger droughts, floods, and heat waves, as well as even stronger storms and extreme weather. So, so then getting into, again, this is sort of the Cliff Notes, we might say, a version of what Leon's going to tell us about, but this is just so you'll have the basic idea of what's behind all of this. So why does aerosols cause more cooling and lead to the conclusion that there's more cooling and more warming from CO2, more cooling from aerosols and more warming? Well, it's because the aerosols currently hide about half of the global warming. And so if aerosol cooling is more than we thought, that means CO2 warming must also be more than we thought in order to have the temperature we observe today. The way I think about it is that, yeah, if this is the temperature we observe today, which is 1.5 C, roughly, and the IPCC says that's because there's this much warming from greenhouse gases and this much cooling from aerosols, so we end up here. But Jim Hansen is saying, no, there's actually more cooling. It's like it's here, and that means the warming from the greenhouse gases must be here. We still get to the same number in between, but it has really big implications for the future if those two numbers are different. Okay, so and I don't know if you're going to cover Faustian bargain. I'm going to just a brief on the Faustian bargain. Hansen has called this extra cooling from aerosols a Faustian bargain, or another way of saying that is our deal with the devil. And what he means by that is a big problem with aerosols in the lower atmosphere is that they only last for about a week or so before they fall out of the air. But our CO2 emissions last in the atmosphere for hundreds to thousands of years. So when we finally stop polluting the world, that hidden CO2 warming will show itself quickly. So, like a deal with the devil, we get some short-term benefit in return for a very long-term problem. With the changes to ship pollution and with the changes to ship pollution regulations, the first Faustian payment has come due, and it's not the last one. And then there's scientists who think this can't be true. What Leon's been saying for years and what Hansen's been saying, that ships can actually have this big of an impact on our global temperature. Some of them say, no, it's not possible because it's only reduced aerosols by like 8% or something. And how can that be true? Well, because it's not just the aerosols that are doing the work of reflecting sunlight. They also act as cloud nuclei, and they create clouds. They make clouds brighter. They make them last longer. And clouds can reflect a lot of sunlight, especially when they're over the dark blue ocean. So the difference between a cloud over the ocean and no cloud over the ocean is, instead of, I don't know the exact numbers, but instead of absorbing 80% of the sunlight, it might reflect 80% of the sunlight. So it makes a huge, huge difference. And as we'll see, Leon's going to show us, most of the warming is over the North Atlantic and North Pacific, where the shipping routes, major shipping routes are. So that kind of is a clue that it's probably due to this versus something else like the Hunga Tonga volcano in the South Pacific and things like that. So, all right. And so one of the other questions that might be asked is, well, wait a second. You said the IMO regulations kicked in 2020, but we didn't see the accelerated warming until 2023. Why is that? And the paper explains that there was a La Nina during that time, during 2020 and up and like through 2022, and therefore that La Nina is a natural cooling phase of a natural cycle on Earth, and so that cooling offset the warming from the ships. And so we didn't really notice it. But then when it switched to El Nino, now the ship warming was on top of the extra El Nino warming, and boom, it was huge. So that explains why there was this delay, supposedly, in the warming from the ships. Um, and some scientists say we're at 1.3 degrees, not at 1.5. This paper concludes we're at 1.5 C now because when you average, this is the projection, that the future temperatures, when averaged over La Nina and El Nino in the future, that average temperature will not be below 1.5. And so therefore, the paper concludes we are at 1.5 for all practical purposes. But people watching this show will know we had several climate scientists on who said, no, we're at 1.3. You have to take a look at the long-term average and all of that. And so why is that? And I don't know what Jim would say, and maybe we'll hear from Leon on this, but basically they're not including the 0.2 degrees of warming from the change in shipping regulations. And if you believe that's the case and that's what happened, well, that's a special bump up, and you should throw it into where we are now, and that would bring us to 1.5. United Nations says we shouldn't go over 2 degrees of warming, and we should try to stay below 1.5. But obviously, we're at 1.5 now. Are we going to go over 2C? And if so, when? And I think Jim, because he's written this, said the Earth doesn't care about imaginary or implausible reductions in greenhouse gas emissions. I mean, you can say anything you want. Yes, if we cut our emissions to zero tomorrow, then yeah, things will be pretty good. But we're not doing that. So he says from a practical point of view, we're going over 2 degrees, probably in around 15 years, plus or minus like 5 years. And 2C is a lot of warming and brings us much closer to these tipping points. And then you might ask, how much warmer does Hansen think the global warming from greenhouse gases is compared to what the United Nations says? And I think we said the United Nations says it's about 3 degrees for a doubling of CO2, or an equivalent of the doubling of CO2. And that would be called the Earth climate sensitivity. And the UN says that's about 3. And he goes into things that they sometimes say it's higher, but when they say it's higher, they're not using their models for the aerosols that they believe in. They're just using these other models. And so when you really look at the models that they claim to be behind, that it's really a 3 degrees of warming. Hansen says it's closer to 5 degrees. So that means for the same amount of greenhouse gases, you're going to get a lot, not double, but a lot more warming than is expected by the IPCC. And then you might say, well, wait a second, we're already at a doubling of CO2 when you consider we've increased CO2 by 50%, and then you add in methane and nitrous oxide and all those other greenhouse gases, you add them together, you get an equivalent forcing of 2 times CO2. So why aren't we seeing 5 degrees right now? Well, of course, one of the answers is aerosols, as we just talked about. They act to cool the Earth. But even so, we're not there yet. And that's because it takes a while to get to that level of warming. It takes a long time. 90% of global warming heat goes into the oceans. And that it takes a long time to heat up the oceans. It's a hard thing to do. And so what you do is you have the heating that we have offset by some aerosols. It cools it down a little bit. And then we have this extra heat that's sort of waiting to warm the Earth. It's called the Earth energy imbalance. It means there's more energy coming into the Earth than is leaving the Earth. And this is by an equivalent of roughly speaking, 1 million Hiroshima atomic bombs worth of energy every single day going off. That gives you an idea how much. And that hasn't heated the Earth yet. That's the heat waiting to warm the Earth. So that's that. And let's see. We talked about that. Let's see. And then we're going to talk later about some of the things we can do about it and the policies we can implement and steps we can take to offset it. So that's sort of the super high level essence of the paper in terms of the claims that it made and sort of the very high level why and whatever. Now we're going to hear from Leon, and we're going to hear a lot more about the background and the science behind what I just told you. So Leon, that's all yours. Take it away.
Thanks, Dan. Get my slides up and share.
Can't see it yet. There we go.
Yeah, just 1 second. Global warming has accelerated. Well, that's pretty clear. And there's a lot of research. Those who have actually looked at the data show that it's unequivocal that global warming has accelerated, both, especially when you look at the ocean heat content. As Dan mentioned, 90% of the additional heat of global warming, let's say. So 90% of global warming is ocean warming. And that happens especially in the top 2,000 meters of the oceans. And if you look at those, of course, if that's the strongest evidence to see whether global warming has accelerated, because the surface temperature, which is measured at about two meters above the surface, there's much more variability there. But if you look at the oceans, it's called ocean heat content, then it's much clearer that the ocean heat content is increasing faster than before. And that's not just me saying that, or James Hansen saying that, or all these co-authors saying that. Even some of the most outspoken skeptics have published a paper in January where they say the rate of warming has increased. A rate of ocean warming is increased. So please look at the actual science, also from the people who say that there's no acceleration, because science shows that there's acceleration, and that is likely due to, of course, the continued increase in greenhouse gas emissions, and therefore continued increase in greenhouse gas concentrations, but also very likely because of the decrease in air pollution, because the air pollution was reflecting sunlight back to space, which I will explain here. So global warming has accelerated. Are the United Nations and the public well informed? Led by James Hansen and his colleagues, Pushka, Karecha, Makiko Sato, or his closest colleagues. George Tsoukalos was on the climate chat a while back, and many other very, very renowned climate scientists are on this paper. Most climate scientists know these names because they are very leading authors. So I think let's start with the first point: are the United Nations well informed? And that's then you have to start with really the basic science. So what drives climate change? And that the unit scientists use, are forcing. So what pushes the climate into a certain direction? I've talked about that before on Climate Chat, and I think it's really important to understand these basics, because that's where everything starts. And that's also, if like I explain it sometimes with, when in my town, people want to know how high the dike has to be. The government, the water boards want to know how the dikes need to be. It starts with the forcings. If the forcings are wrong, everything is wrong. So you really have to start there. So what are the forces? What forces the climate change? Of course, everyone knows about carbon dioxide. So these are IPCC forcings updated by Forster using this IPCC methodology. Forster was also lead author of the IPCC report, the first assessment report. And then you see carbon dioxide, of course, is the leading cause, the leading forcing. But there are other forcings, which are methane, nitrous oxide, halogens, and ozone. Ozone is also forcing, which is also caused by other greenhouse gas emissions, but it's a forcing in the troposphere. So in the first 10 kilometers from the Earth's surface in the atmosphere, the first 10 kilometers high, not stratospheric ozone. And then, but stratospheric, which is the layer where the ozone layer is, let's say, where the ozone absorbs UV radiation, which many people confuse with climate change, but it's different environmental problem, right? The decrease in ozone in the stratosphere. But in the stratosphere is also water vapor, and that's caused by our methane emissions, which cause the concentration of water vapor in the stratosphere to increase. But that's very small, that effect. And there's albedo, which means reflectivity of the planet. So the land use changes. If a forest is removed, then there's, for example, crops growing there, or other more reflective surfaces replacing the forest, then you decrease the albedo, and other way, and if you have a more reflective surface, you increase albedo, for example, through desertification. And the net effect is that more sunlight is reflected back to space because the reflectivity of the surface increases. That's also forcing. That doesn't include ice, melting of ice, because that's a feedback. I'll get to that. And then, of course, there's light absorbing particles. So if you emit soot and the soot deposits on ice, that's a forcing. That forces the regional and in the end a global warming to a certain extent. It's also very small. And then airplanes flying at high altitudes, creating these very thin clouds. They are called cirrus clouds. And they cause a bit of warming because they reflect more long wave radiation, so heat radiation back to the surface, then they reflect sunlight back to space. But then there's aerosols, and that's the main subject of today. There's a very strong cooling effect, so a negative forcing, which pushes the climate, especially over the northern hemisphere, into a more colder state. But of course, the greenhouse gases are winning. And this black line is important because that shows the uncertainty. And as you can see, the uncertainties of the other forcings are not so large. But the main uncertainty is here, is with aerosols. And that's why we say the biggest uncertainty within climate science is aerosols, especially aerosol cloud, which means the effect on aerosols on clouds. So the main part of aerosols, about 80% roughly, is the effect from aerosols on clouds. So if you say that the climate sensitivity is high, I'll get to that. You think this is low. So the aerosols were cooling only a little bit, hiding only a little bit of the greenhouse gas warming. And if you say that, if you think that the climate sensitivity to greenhouse gas and to aerosols is high, that means aerosols have been cooling more. Otherwise, you would have seen more warming by now. And there's solar. There's some variability, that's in 2023 compared to 1750. So that means that in 2023, the sun there's this 11-year cycle. The sun was shining a bit brighter in 2023 than in 1750. And that the unit used here, I forgot to mention that, is watts per square meter. And the Earth has a surface of 510 million square kilometers, which means 510 trillion square meters. So that's a lot of meters. And a watt is a joule per second. So every second, these forcings are either adding a lot of heat into the Earth system by absorbing long wave radiation and keeping the warmth inside, or when we talk about aerosols and the effect on clouds, they reflect that much globally on average sunlight back to space. So that's the point. So is the UN wrong? We have to start, of course, with what does the UN or what does the IPCC say, and that informs, of course, the UN and then the general population. And then again, these forcings, if you graph it on from 1750 to today, you see again, let's say start with carbon dioxide is the main greenhouse gas. So a large part of the total anthropogenic, total human caused forcing is from CO2. And these are all the other forcings. There's also volcanoes there. So if there's a strong volcano goes off, like Mount Pinatubo in the 90s, you see that it's here, and then the net effect is even negative. You see, so the total effect of all these anthropogenic force. Sorry, that's a total effect. The thin black line. Total effect, including anthropogenic forcings, was even a bit negative after Mount Pinatubo erupted. So temporarily compensating for the thick black line, the anthropogenic forcings. But then there's this line, so CO2, long-lived, pervasive in all sectors, persistent and irreversible global warming. So it's hard to take the CO2 out of the atmosphere. That causes long-term warming. For example, methane has a shorter atmospheric lifetime. So if we would theoretically immediately stop emitting methane, the concentration of methane would rapidly decrease. But that's for now, that's theoretical. The methane concentration is record high. But then you have SO2, which means sulfur dioxide, which is short-lived. It has a lifetime of sulfur in the atmosphere, has a very short lifetime, rains out quick. And that means that if you reduce this, that's also the IPCC saying this, right? If you reduce this, there's more warming. And this says aerosols, the tropospheric aerosols, but sulfur aerosols are about 100% of the aerosol effect, because some other aerosols cause cooling, some cause warming, like black carbon soot deposition on snow, as I already mentioned. So that's why sulfur causes most of the cooling, most of the negative aerosol forcing. So what does the IPCC say about climate sensitivity? So you have this forcing, this forcing that pushes the climate into a certain direction, but how much warming that causes depends on the feedbacks, which I show here. And this is also IPCC graph. So what IPCC says is the Earth climate sensitivity is 3 degrees, with a likely range of 2.5 to 4, and a very likely range. So that's the broad, I think that's a 95% certainty range, that the sensitivity of the climate, and that means to a doubling of the concentration of CO2. That's how climate models use that often to test to estimate what will be the warming effect of doubling the CO2 concentration in the atmosphere, and the effect of that is so between 2 and 5 degrees, according to the IPCC. And why is that? Because so the total effect, that means that if the Earth warms, the different feedbacks start to act, and one is that if the Earth heats up, it starts radiating more heat to space. If you for example, if you have a metal in the fire, you see it starts glowing red. That means it's very hot. That means it's radiating a lot of heat. But if it's not that hot that it will be red hot, you can see it with an infrared camera. You can still see that there's a big increase in how much heat is radiated because the temperature is high. So and that happens with us as well. We radiate heat, the planet radiates heat. So and if we are warmer, we radiate more long wave radiation, infrared radiation, which our eyes can see, but it's really there. I'm sure I can show you maybe one day with my infrared camera. So that you see then that every degree Celsius of temperature increase of the planet, there's an estimated increase in outgoing long wave radiation of 3.2 watts per square meter. And that it's negative because that lowers the amount of heat in the Earth system by radiating more heat to space. So that's the Planck feedback. So this is really crucial aspect of understanding the climate system, is that when things get hotter, they radiate more heat. And then we have the water vapor feedback. And then there's also the uncertainty is there's not much uncertainty there. And then we have the water vapor feedback. And that means that if the atmosphere gets warmer, the atmosphere can hold more water, and water is also a greenhouse gas. And that causes in the troposphere, so in the bottom layer of the atmosphere, that causes more heat to be absorbed from that increasing Planck feedback, right? From the radiation that's going out. So that water vapor is really a crucial aspect also of the climate system. One person, I don't even know his name, but was cited when our global warming in the pipeline paper came out by some media saying they don't take into account, James Hansen et al. Don't take into account water vapor, which is really a ridiculous thing to say, because of course they take into account water vapor. If you make a climate model, you don't take into account the effect of water vapor increasing, you cannot, your model will be completely off, of course. And it was again this same person saying exactly the same thing 2 years later, that James Hansen didn't take in this new paper, also didn't take into account water vapor, which is, I think, quite strange thing to say, let alone for the media to cite. But yeah, just to explain this, you need to take that into account. And of course, models take that in, every climate model takes that into account. And then the next is surface albedo. So the changes in the reflectivity of the surface. And that is mainly the effect of melting of ice. So if the Earth gets warmer, ice starts to melt, and especially starting from the lower latitudes, of course, and closer to the poles, it will take more warming for melting to start, and snow starts to melt. So that changes the surface albedo. So this is also a feedback. The mentioned it's a forcing, but it's also a feedback. And there's quite some uncertainty there, but the biggest uncertainty, again, also for feedbacks, not just for forcings, is clouds. Very big uncertainty in what clouds do. Well, it could be positive. So if it's warming, it could be negative, which means that if it's warming and clouds evaporate or increase in altitude, they absorb less solar long wave infrared radiation, which cause more heat to go out. So that includes that, but also, of course, if you decrease cloud cover, as George also mentioned to Dan in the climate chat, the cloud feedback causes less sunlight to be reflected back to space. So if there's warming and there's less clouds, smaller clouds, or because again the atmosphere can hold more water and it condenses less quickly, then you can have an increased a decrease in cloud cover, which means more sunlight will be absorbed. And this together with the uncertainty of the aerosol cloud forcing, you can understand that it's quite difficult to say this is caused by warming, there's less clouds because of warming, or there's less clouds because of a reduction in air pollution. And then there's biogen, but it's quite uncertain, but it's almost negligible. So what is the total effect? I look back here, I showed you this last time we talked then, and if people want to know more about these graphs, they can look at that, but just in very short, this shows greenhouse gas forcing relative to 70-50, going back 130,000 years, and you see that there was a greenhouse gas force, a decrease in greenhouse gas concentration in the atmosphere about 20,000 years ago, and that caused a forcing decrease of about 3 watts, negative forcing of 3 watts. And now we have increased the greenhouse gas concentrations equal to what would happen if you would double the amount of CO2 to about 560 parts per million, and that causes a greenhouse gas forcing of about 4 watts. But if you take into account aerosols, also looking back at 6,000 years, because we've been burning stuff for much longer than since the Industrial Revolution, then this image changes, and we think, and was also part of global warming in the pipeline paper, that you have to take that into account, and of course then you have to take into account the aerosol forcing we still have now from industrial activity, and then you have about 3 watts per square meter total force. So now, what does the paper show? Right? They show the data from NASA satellites that there's a big decrease in how much sunlight is reflected back to space. And it's a decrease of about 0.5 percentage points, which means from the total, there was about over 29%, and now it's less than 29% of the sunlight reaching the Earth being reflected back to space. And that might not seem like a lot, but that really is a lot. It's a lot of energy being, a lot less energy being reflected back to space. And then here, this is again a graph from the new paper where they show the zonal mean absorbed solar radiation. So what does that mean? This is since 2000 to 2024, and this is by latitude. This is the satellite data from NASA. Again, where they show that there's a big increase in how much sunlight is absorbed, especially over the recent years, over the northern hemisphere, and then where many of us live, of course, and then at the mid latitude. So that's important to take into consideration. And why is that? So I've talked about this before, and this is what the paper is mainly about, right? The sulfur emissions from shipping. So what happened? Global shipping saw a decrease in how much sulfur was allowed, and that was implemented by the International Maritime Organization, where about 200 countries, 190 countries agree on the regulations where they say, okay, we have to reduce air pollution. And starting here, for example, near where people live around North America and over the North Sea, where they agreed that the sulfur emissions from shipping had to reduce in 2015 from 1 to 0.1%. And that means that the ships had to use cleaner fuels or use scrubbers, which means they scrub the sulfur from the exhaust gases. And then if you look at the top graph, which is in parts per trillion, which might not seem like a lot, but it's quite important, with total sulfate, which are these sulfur aerosols, globally. And then you see that, of course, over India and over China and also Europe and the United States, and but also over the oceans, there was a lot of sulfur being emitted. But it includes natural sources of sulfur. But how much of that was from shipping? And then you look at over land, and of course there's little ships there, and there's not a lot of sulfur being emitted over land, which makes sense. But over the oceans, about 70 to 80%, especially over the North Pacific and North Atlantic, 70 to 80% of the sulfur over these regions was from shipping. And that's all. There's also natural aerosols, natural sulfur being emitted by algae, but they need nutrients, and there's quite some uncertainty about how much these algae emit. But you can see, taking that into account, that the main source of sulfur over the North Pacific and North Atlantic, but also over the other regions, was from ships. And then if you reduce that by a lot, that results in less particles in the atmosphere, less cloud condensation, as we call it. So these to make clouds, you need small particles for the water in the atmosphere to condense against and to create clouds. So it's important to have these particles also from natural, but also from natural sources like algae, like pollen from trees, like sea salt, etc. But we increase this. So that's also important to mention that the background source is different from our source. The background, what was already there, we don't consider that a forcing. For example, when you talk about greenhouse gases, most people will understand that all these volcanoes, that's just nature. That was there, and that didn't increase the greenhouse gas concentrations much. But now that we are starting to have started to burn fossil fuels, then you start to increase the amount of CO2 in the atmosphere, because that's an added source. And the same, it's the same with sulfur, with aerosols. It's the background load, what we call the background load. So what's already there is not a forcing. That's just what's there. But if you add something, that's what we call forcing. That changes stuff. That changes things, right? So if someone says there's already algae emitting sulfur, it's like saying, yeah, there's already volcanoes emitting CO2. That's quite a strange thing to say to say that this doesn't play any strong role, right? So you really need to take that into account. And then again, let's look at the main regions where this study looks at, because they used this to estimate the global forcing. So these regions, it is the North Pacific Ocean and the North Atlantic Ocean. You see that's mainly from shipping, as I showed you. And these are the region, so that's between 20 and 60 degrees latitudes over the Northern Hemisphere. And this is global, and this is over these latitudes. And this is a total global over these latitudes. So that includes also, for example, the Mediterranean and other regions. But the new study by James Hansen et al. Takes a look at only these regions. So that of course they take a look at the global changes, but they to estimate the aerosol forcing change from the shipping emission reductions, they look at the North Pacific and the North Atlantic, and they extrapolate that to a global effect. And that's why I think it's important to note that over these entire latitudes, so including the Mediterranean, that's 50% of the emissions. So I think that's why it's of course not perfect, but working with the limited data we have now within 4 or 5 years since this regulation came into effect, if you want to make an estimate, I think this is a valuable way to do it, to estimate it based on data, not just models, but really based on data to make an estimate of how big could this effect of these sulfur emissions reductions be. That's what they did, and they looked at these regions, and that's less than 50% of sulfur emissions from shipping happened over the North Pacific and the North Atlantic Ocean. And then what we see, so over the entire region, there's a very strong increase in sea surface temperatures, but the real increase in how much sunlight is absorbed is really over this region, over the north, especially, for example, in the east of the North Pacific. That's an increase of 10 watts per square meter. And that's really a mind-boggling amount. That's 100 kilowatts of energy per hectare, which is really enormous. So that region, and this whole region, absorbs so much more heat, a lot of heat. And then it's not surprising. That the same latitude sees a very strong increase in sea surface temperatures starting in 2020 when this regulation was implemented.
And Leon, I think this is such an important graph, and the more you know about it, the more amazing it is. But maybe you could actually talk about what this graph is showing us, and like,
yeah, good point.
Yeah.
Yeah, so I already told you when I showed you so I showed you already this one. Wait, going back. this shows absorbed solar radiation anomaly. So the increase in how much sunlight is absorbed over these regions by latitude and since 2000. And this shows the zonal mean sea surface temperature. So the changes in sea surface temperatures over the same period in time. So between 2000 and 2024.
But every point though, like first of all, it goes up to the North Pole, down to the South Pole,
Yeah.
and but every point is the average temperature anomaly over the ocean over the entire latitude.
Yeah.
Yeah, so you're sort of getting the global average at every point, and then the bottom line is showing how it varies with time.
It's a regional anomaly. So if I don't know the baseline here, but so what I often show is that so over this region, over the northern hemisphere mid latitudes, the warming over the past 15 years, the temperature increase over the sea surface temperature increase over this region was more over the past 50 years than in the preceding 150 years. And this is also the reason why we have quite a lot of data, because of course that's where already before the industrial, already over the past 200 years, there was a lot of shipping happening, and the ships, they took temperature measurements from the oceans. So that's also why this region is also quite reliable. And that's really I think that's really worrying, because of course this is also the region which impacts our weather, the regional climate, very much, where in this region where most of us live, right? I don't know
Right.
where all the listeners live, but I live at 52 degrees latitudes, and Dan lives a bit lower, but also within this bound, and that's really important to mention. And I think that's when you look at the media, when you look at discussions, or some people who are skeptical about it, they are skeptical maybe about the global effect, and a lot of discussions are about the global effect. But I think, to me, living in this region, but I think for everyone globally, the regional effects are much more important than the global effects, because we don't live we don't care if it's 1.5 degree warmer globally. We care what happens regionally where we live and where we grow our food. So that's really crucial. And of course also where the ice is and when the ice is made.
But I also want to go back to the elements. I also want to point out that those red blobs in the center, in the middle, at the zero, that's El Niños showing up. And then when you get the yellow and the light orange, whatever, those are La Niñas. And you can kind of see the La Niña on the right side, right before. You can see the heating caused by the ship emissions rule in 2020. It's the red area at the top. But you say, well, why didn't we see it? Well, there below it, there was a cooling La Nina. And then finally, around 2023, the El Nino kicked in again in the center. And now that was added on top of the warming from the ships above it. And you can kind of think of that warming from ships as like a permanent El Nino going on now.
Yeah, so
And
that's what
really
Makiko
adding
Sato,
the
one of the long-time co-authors of James Hansen, she recently retired, but she also was co-author of this study, and she called that indeed Northern Hemisphere mid-latitude permanent El Nino. So it's really, and indeed that's what many were questioning. So why do we only see it in 2023, this global temperature peak? But if you take into account the El Nino cycle, you could already see that there was an increase in the rate of warming. And then if you look at the regional effects, especially over the oceans, I think the image is quite telling, right? That you see that it didn't start in 2023. It worsened over time, because it takes a lot of time for the oceans to heat, and of course, as I showed, some feedbacks come into effect. But this is the main region where this happens, but it is global. So of course, ships have sail around the world globally, but this is really the main region.
And the warming at the southern area there is there an explanation from that? Could that be the melting of the Arctic sea ice, or is that
Here's
shipping? Or
cooling. This is
no, that
Arctic,
red.
the
Okay.
Antarctic. This.
Yeah.
Yeah, so it's that's a good question, and of course there's again over the southern hemisphere there's also a lot of clouds over the oceans, and if the ocean's warm, if there's more heat accumulating in the system, and maybe I think maybe and more it seems more and more likely that less heat is transported from the Southern Ocean through the Atlantic through the Northern Ocean and North Atlantic, keeping more heat in the South Atlantic. And
The AMOC slowing down.
and that's the AMOC.
Yeah.
You had a guest on recently who was questioning a bit or saying talking about the other ocean currents and saying that the other ocean currents transport a lot of heat as well, like the Gulf Stream. But that's true. The atmosphere also transports a lot of heat around the world. But what's important to note is that the Atlantic Ocean is the main. So the AMOC, the ocean current from south to north, that's where heat is transported from the southern hemisphere to the northern hemisphere. And that's also what James Hansen talked about. He told me when we met in The Hague recently, and he talked about it again during his presentation of the new paper, is that this the amount of heat transported before slowing down through the Atlantic Ocean from the one hemisphere to the other hemisphere is about 1 petawatt, and that's it's a one with 15 zeros, so that many joules per second. It's hard to comprehend how much that is, but it's the same as the effect of over one hemisphere of doubling the amount of CO2, which is 4 watts per square meter. So it's 510 trillion square meters divided by 2 and then times 4 watts. So that's really an enormous amount of heat. And of course, that's now already the greenhouse gas forcing we have globally is 4 watts, as I showed you. But then if more heat stays, if less sunlight is reflected back to space over the northern hemisphere, and that causes more heat to accumulate over the northern hemisphere, that means also that there's less heat has to be transported from south to the north to create a hemispherical energy balance. So between the two hemispheres to keep temperatures more or less in line, right? So that's really a crucial aspect, and it's not just me saying, but there's quite a lot of research showing that aerosols, especially if they are emitted over the northern hemisphere, sulfur aerosols emitted over the northern hemisphere, were reducing the weakening of the AMOC. That's really important to note.
Okay, very good. Thanks.
So that's just, I showed you absorbed solar radiation, but as I mentioned, if temperatures increase, there's more heat being radiated to space. So that results in an energy imbalance. So the energy imbalance is absorbed sunlight minus outgoing long-range radiation. Absorbed sunlight minus the increase in outgoing infrared, and then if the increase in absorbed sunlight is more than the increase in outgoing long-range radiation, there's an increase in how much heat accumulates, which is the energy imbalance. And then you see that also over the same region where we saw the big increase in absorbed solar radiation, you see that there's a big increase in heat accumulation, a big increase in the regional energy imbalance, and that's still increasing. So I think that's maybe even more. That's really worrying, right? Because of course, when we started doing this research, we started looking at all this data. We didn't know what to expect. We said it might be the effect might be strong, but it might also not be strong. But now the data is quite worrying, as George also told you, that there's also the feedback to take into effect. right? If you look at here, for example, this is the effect of the El Nino likely, where you see in the tropics, the warmer tropics showing less cloud cover because the oceans are warmer, and then you see that more sunlight is absorbed, and then you have to look at these different what we call fluxes to understand what's happening. So yeah, and that's important. If you just look at the net effect, that's interesting, but you also have to look at these different the differences between, so what causes this effect, right? And that's what I show here globally. So there's the black line shows absorbed solar radiation change. This again, it's all units in watts per square meters. In again 510 million square kilometers. So this graph I have this graph for different regions, but this is of course 100% of the Earth's surface. And the data came in last week until November. So we don't have all the data for 2024 yet, but this shows an increase, very big increase of almost 2 watts in absorbed sunlight, but also an increase in outgoing long wave radiation. Even if greenhouse gases and water vapor from the water vapor feedback increase, there's an increase in outgoing long wave radiation, but there's a relative decrease because there's much more. This increase in absorbed sunlight is much stronger than the red line outgoing long wave radiation, and that means that over the past 20 years, so as long as these satellites have been looking at the Earth and taking measurements, there's an increase in how much sunlight or how much heat accumulates globally of 1 watt per square meter globe. And that's really, really mind-boggling. That means that we could have a lot more warming in the pipeline, as James Hansen and where I was co-author, previous paper was called. So it almost looks like a pipeline, right? So it's really there's much more heat coming in. There's much more heat coming in, which will result in much more warming.
And
just
to
quickly
give that
mention-
number, let me just to give that number, I did the quick calc here. The 1.37 watts per square meter doesn't sound like a lot, like a tiny light bulb across each square meter. But when you add up, it adds up to be about the energy equivalent of over 900,000 Hiroshima atomic bombs going off every single day. That's how much extra energy is coming into the Earth than is leaving. And when you imagine 900,000 Hiroshima atomic bombs going off every day, you can kind of say, wow, that does seem like a lot of energy that might be doing something to the Earth over time. Again, every single day.
Every day, yeah, exactly. So I did a calculation as well, and December 2020 was quite low. Was relatively low compared to other December. So I expect this number to increase, and then the 4 years since 2020 to end up using this data set above 1 million Hiroshima bombs worth of heat accumulating into the Earth system every day for the past 4 years. And that's, it is impossible for us to comprehend how much heat that is. 1 million, so that's 4 times 365 times 1 million Hiroshima bombs accumulating in the Earth system in 4 years' time.
Eli, you had a comment?
Yeah, I just wanted to mention while that graph was up that you look at the slopes of the total versus the re-radiated heat, and the re-radiated the slope of that, the rate of change, is outpaced by the increased forcing. And that is you look further back at the graph, and they tend to match much more closely up till about, I guess, 2010.
Yeah, 2010, and then here you see that it's really starting to diverge a lot. I cannot make can get the graph for the energy imbalance up later. But, yeah, that's really, this is where a lot is happening. In what James Hansen showed, like since 2010. That's also that's also what NASA showed, and what NOAA showed, that and even what some of the skeptics show, that over the past 20 years, the rate of heat accumulation in the Earth system has doubled. And it looks like it has more than doubled now, right? With the most recent data, that's more than doubled. So that's really and then you can only, like, it would be very strange if that wouldn't lead to an increase in the surface air temperature. So what many call global warming. I call global warming ocean warming mainly, because that's 90% of global warming. But many also talk about surface air temperature increase, which will also, of course, and we shall already see it clearly, that there's an increase also in the rate of surface warming. But now back to the main conclusion, and you can see it maybe behind me here. I wrote down 0.5 watt per square meter increase in forcing from shipping. That's the main estimate of this study, where they show, okay, global warming has accelerated mainly because of the aerosol forcing from shipping, and of course, behind it all is the continued increase of greenhouse gases, which this paper also, of course, highlights very clearly, and it very clearly mentions we need to reduce greenhouse gas concentrations, and of course, to do that, you first need greenhouse gas emissions need to go down, which is still not happening. I think Dan can talk more about that when he talks about policy. But so, and then the feedback, again, mainly clouds. So that's over the observation period of this data, the cloud feedback is estimated to be over 1 watt per square meter. So that's stronger than the effect of the shipping emission reduction, more than two times strong. And that is also very worrying, because that means that the climate sensitivity is higher. And in a way, it doesn't matter very much. In my opinion, of course, it matters a lot for the science, and if you want to understand it and you want to get the numbers right. But those who have to live with the consequences, it doesn't matter a lot if the increase in how much heat is accumulating in the system is due to cloud feedbacks or forcing, right? The effect is the same. More heat accumulates in the system, faster melting of ice sheets, faster melting of snow, which also decreases which is also indeed here, snow and ice feedback is a feedback. And then, but it also increases sea level rise. And then the atmosphere is now warming 4 times as fast as before 2000, which means much stronger storms, much more extreme rainfall patterns, but also extremer droughts, because the extremes get more extreme when you increase the heat in the Earth system. And that's, yeah, so this is the finding based on the region. And so in this region where less than 50% of the shipping emissions happen, they was about close to 0.5 watt increase in absorbed sunlight, and they extrapolate that to the global average by taking that effect as a global estimate. And I simplify it a bit here, but that's simply what happened. Simplified what happened in the study, where they look at these main regions where we expect a strong effect, and then extrapolate that to the global average. And of course, it's not a perfect methodology, but it's much better than just taking a simple model and making an estimate. Well, the uncertainties are so enormous, and we really need to base the estimates on the available data. That's really crucial. And the available data, these NASA sea satellite data, but also the sea surface temperature increase, are very worrying, and I think it's really enormous. It's a very high estimate. It's the highest estimate. It's 5 times higher than some other estimates, but we shouldn't. We should really take this seriously, because this is really what this could be the real effect. Because there's, especially going further back, there are more studies showing this could be the range, and that's because, of course, these ships were cooling or reflecting sunlight over the dark oceans, which now absorb much more heat. And then going back to the main question, so is the IPCC method, is the UN misinformed, which is mainly, is the IPCC forcing estimate wrong? I think it's very wrong. The IPCC forcing estimate for 2023 was the lowest in 8 years. I've mentioned this before. Well, the absorbed sunlight was 2.3 watts per square meter higher in 2023 than the first decade of this century. And that you cannot align those two, right? You can say, okay, this is a big part of this is feedbacks, fine, but there's no way in hell that the aerosol forcing now is lower in reality than it was in the preceding like 5 years before, for example. And why does the IPCC methodology get this number? Because they don't take into account where these aerosols, where this pollution happens, and they assume that forest fires, for example, Canadian forest fires, are just part of the global average, and they should also just fit it all into this simple model, and they get one result out, which is wrong, which is completely wrong, because the forest fires over Canada don't happen everywhere over the North Pacific and over the North Atlantic like the shipping emissions do, right? And that's just one example, but this is really crucial to take into account. And of course, the effect is global. This just shows a global effect, which also, as I mentioned before, doesn't show the regional warming effects, and that's also crucial, because the effects, the harm will be done where these emissions reductions happen. So the most of the harm will be done where these emission reductions happen. So again, I think that I'm not saying these are not serious scientists, because these are really, many of the leading scientists have co-authored this paper by Forster et al., where they show, it's called Climate Indicators, where they try to update every year the IPCC methodology, which is really a laudable thing to do, because we do need annual updates, but they don't take into account the satellite data from NASA, which is really a crucial indicator, which you cannot miss. And they should take that into account with their next update. And then I think the numbers will change a lot, and that will have a lot of impact on climate science around the world, but also policy change. And I think that's really an important paper to look forward to see what those estimates are. And I think it's also important to be very vigilant, because their last 2 years they pushed that paper through the peer review process to be on time for the UN meetings, and I think that's they should be informed in time, and I hope some of them are watching today, but I've mentioned that before. Again, here, lowest in 8 years, effective radiative forcing from aerosols. So yeah, I'm almost done here. Again, North Pacific, this is 4-year average, and that's really an enormous increase since 2000 to 2004. So there's an enormous increase in how much sunlight is absorbed in this region, more than 4 watts per square meter. And again, even if there was a lot of warming in this region, which of course increased the outgoing long wave variation, as the data shows, there is still an enormous imbalance over the past 4 years, which means there's still a lot of regional warming in the pipeline. And this increase, many asked before why this is. I made a graph, but it's also part of in a different graph, part of the global warming has accelerated paper, where it showed the Pacific decadal oscillation, which is a cycle, natural, but maybe it also has something to do with this air pollution of the Pacific Ocean, where it changes a bit where the sea surface temperatures are warmer. And this index shows that when this index was high, so 0.5, that also coincided with the increase in regional absorbed sunlight. But now it is the lowest, I think I have this here, yes. So it's the lowest it has been since 1880. And this is also the 4-year average. So it's highly negative, and I think that's in part also can be explained by this. Looking just at, and that's also what a NASA study estimated, that if the Pacific decadal oscillation would be negative, we would see a decrease in both absorbed sunlight, especially over this region, because of course it increased when it was positive. That's why they estimated that. They estimated that it would decrease when this would become negative. But as this shows, it has increased to record high values, while Pacific decadal oscillation is very strongly negative. Again, the most negative that has been since 1880 I think both for 1 month, for 1 year, but also for 4 years on average. And that's really crucial to take into account. And also maybe so if it becomes positive, we could have even much more warming and more heat accumulating in the Earth system. This is really worrying. Maybe it's very technical, I think, for most people, but this is a really worrying graph, really worrying number. And this is the North Atlantic, which also shows not quite as much as the North Pacific, but it also shows a really, really enormous increase in how much sunlight is absorbed. And that also, again, since 2020, that started to really increase, and the outgoing long wave area hasn't catched up yet. So that also means that for the North Atlantic, I think, especially compared to the past 4 years, we can see still quite a lot of additional warming in the pipeline for the North Atlantic, or maybe a decrease in how much heat is transported from the south to the north. I think you want to go to policy, or should I also cover the AMOC, or are you going to cover that?
Well, I mean, this is the things we could do to help the AMOC, or are you just going to talk about the AMOC that was losing strength? And
I think, these are the drivers, but I think we've discussed it before, and I also had some other updates. But I think that,
Well, I think it's important to say, maybe we'll just talk about it now, and both you and I. So one of the things in the paper is
sharing.
Okay. One of the things in the paper is that Jim Hansen actually, in what I think it was 2015, wrote this paper, Ice Melt, Superstorms. I can't remember the whole title, where he talked about
global warming. 2 degrees is dangerous. I think that was
2 degrees is dangerous. And one of the reasons it's dangerous is because he predicted back then, and this is when you got to remember the IPCC has been saying and still says that the chance of the AMOC collapsing this century is very unlikely. I think is the words I use, like very unlikely. Very like just a 1 or a few % chance of it happening this century. And Jim said back in 2015 that no, that's not true, because the acceleration of ice melt from Greenland and the Arctic is putting a lot of fresh water in here, and it's a higher amount than what they're assuming, and it will be a higher amount. And he's kind of right about that. And he also said that the mixing, the other scientists, and we had Gavin Schmidt on here talk about it actually, saying that no, there's so much mixing that any fresh water that's there on the surface gets mixed in below, and so therefore the effect of the fresh water isn't very high. And Hansen said, no, that's not true. That's an assumption that's not correct. And when you use this assumption that not as much mixing, you get a much faster AMOC collapse. And I actually looked up the papers too that he was talking about, and he said that the ones that have low mixing do a better job of what's called hindcasting, or looking at the past. You run the model, but you run it backwards and you say, what should have been? And then you look at what it really was. And then you can look at temperatures and all this kind of stuff. And the ones that have the mixing that Hansen was talking about, the AMOC collapse faster. And those are the ones that match the historical data better as well. So that was a big clue. And then in the last couple of years, there's been, and we've had all these people on Climate Chat. You can look up Peter Dibblitzin, Renee Van Vesten, and Gabriel Pontes.
Yeah.
All looking at statistics showing that the AMOC is collapsing faster, physical models with Ray Van Vesten showing that the AMOC is collapsing faster. And with Gabriel, it was observed data showing that it was collapsing faster. Now, I should say there's also a few papers out there that say, no, the AMOC is not slowing down at all and everything is fine.
Yeah, I think that what's important to note that one paper showing that was didn't take into account the past, I think, 7 years.
Yeah, you got to be really careful when you look at these papers, because people say, no, this paper says it, and then you got to look at what the assumptions are in the paper, and it turns out.
Yeah, you have to look at what it actually says.
Yeah. So that was one of the, I know that was that one paper that everyone brought to my attention. Oh, no, it says there's nothing wrong. It didn't really cover it really well. So Hansen, I'm going to bring up something. There was this webinar when the paper was released, and Jeffrey Sachs, who well-known economist, policy person at Columbia, said at the end of the webinar, says, I've spoken to 1,000 climate scientists, he said, and I can tell you that Jim Hansen not only is right most of the time, but he tells us these things way before anyone else does. And this is an example of that, where AMOC collapses in the news, well, unfortunately, not really in the news, but at least among climate channels being discussed as something serious. Yeah. And yet this was 2015 when he brought it up. And now it's only, it's like 10 years later that the rest of the world is catching up with that. So I don't know, when Jim Hansen tells us something, I think we should all listen. It doesn't guarantee he's right about every single thing, but exactly. What he does do is he looks at the climate from a systems point of view. He's not like this cloud physicist who's just modeling some nuclei and looking at some ice particle interaction. I mean, he relies on all the other scientists for the details of that. But he knows how to put it together in a big picture, something that Leon does as well. And looking at the big...
And he brings those scientists who do look more at a specific part of the system. He brings them together. So those scientists are co-authors of his paper, which means that those scientists read this paper and provide feedback, and that estimates are changed during the writing of the research, and only then these conclusions are drawn, right? And I think that's what many people who don't understand these processes don't understand, and you see all say, okay, James Hansen says this, but it's not just James Hansen saying it. It's James Hansen and his, I think, 17
other co-authors, 17 co-authors.
Yes, colleagues are saying this and presenting the data, and the data is saying this, right? It's if you present the data and you say this is what the data shows, and then someone has to, if you want to counter the points made by James Hansen and his colleagues, you would have to either prove the data wrong or give an alternative explanation of why the data is what it is. And I think that's all most often is not really done here. right?
Right.
There's a lot of discussion. No, he's wrong, or some even imply that he is exaggerating on purpose, which is really not true.
It's not true.
No, it's really. I think looking at what what we wrote, because we wrote many, not just the global warming in the pipeline paper, but also these monthly updates. If you look at that, I think if you look back at it, I think that's also quite some underestimate, because of course we didn't know what would happen. We would have thought, for example, that we would see in 15 years time more warming in over the northern hemisphere, mid latitudes, than in the preceding 150 years, right? That's like beyond, I think, what we thought what would happen here. We just understood what forces the climate change. We understood what are the drivers of climate change, and then we presented them and we said these are crucial indicators, especially the satellite data, are crucial indicators to have an early sign of what is happening. And now, and those signs were very worrying, but they are still increasing. This, as I showed, this absorbed solar radiation is still going up, and this imbalance is still increasing, and that I think is really quite worrying. And yeah, that's not what I think what we expected, and that's also that's what we show now, right? So and based on the data, we say it's very worrying, and that shouldn't be downplayed by anyone, especially not without any evidence to back it up.
Right. And the thing is, I mean, even if you want to discount what Hansen is saying a little bit, we don't accept this level of risk in any other part of our lives. We would never accept the probability of our house burning down is, 10% a year or something like that. That would be insane, right? And or the chance that our plane would put our child on a plane and it had a 33% chance of crashing. I mean, it's like the climate scientists saying, well, the median chance is that it's going to be fine. Wait, that's a third of a chance of crashing. You would go out of your mind. You would do everything to stop that from happening. And look, the first plane crash, there was one right afterward, but the first commercial plane crash in 15 years in the United States. And everyone is going, oh my God, how can we let this happen? How can we let this risk of 60 people
some people
dying?
want to fly anymore,
and yet
right?
we're allowing much, much greater risk that, by the way, continues for thousands of years. The risk is not like a one-time thing. And we just pass it off as, well, I don't know, let's cross our fingers and hope things will be okay. You don't do that any other part of your life. Why are we doing it here? Now, there's a lot of reasons. We talk about, I have a whole show on barriers to climate action, which talks a lot about the psychological barriers to why we won't engage on this problem. We have a lot of programs to back that up. By the way, speaking of upcoming programs, this kind of relates to what we're talking about today. Next week, let's see, we have Dana Nuccitelli of Citizens Climate Lobby. Citizens Climate Lobby is one of the groups that advocate for the fee and dividend carbon price, but they also do some other things, and we're going to learn all about that next week. And then a few weeks from now, we're going to have David Fenton on again, one guest we've had a couple of times, who's an expert in how to communicate about climate change and things like that, because we're obviously not doing a good job of that. And other guests. And by the way, I forgot to say, but please like and subscribe. Please follow Leon and myself and Stacy and Eli on Twitter and Blue Sky, and links are in the description. And let's start talking about some of the solutions that Jim talks about.
Can I just like?
Oh yeah.
Wait. So what I didn't mention, and that's crucial also for the point on. So the main question was: is the UN wrong? And is the United Nations, or are people misinformed, right? And I think that really relates again to this climate sensitivity. And I didn't tell you yet the conclusion of this research, but also on global warming and pipeline research. And also recent research, for example, from Jessica Tierney et al., I think was published this week, is that the climate sensitivity estimate, based also on paleoclimate data and other indicators, is 4.8 degrees Celsius, about 4.8 degrees Celsius of warming per doubling of CO2. So if you would double the concentration of CO2 in the atmosphere, that will cause a forcing of about 4 watts per square meter globally on average, and that would cause a warming effect of about 4.8 degrees Celsius. And of course, as I mentioned, we have already doubled the amount of CO2, or we have already increased greenhouse gas as much as we would have, what would happen if we would double the amount of CO2. And the aerosols are still hiding part of that. But that's, but that's rapidly decreasing. And with this climate sensitivity showing more and more estimates showing that it's likely on the very high end, because that was a very likely range, right? That's 95%. So it's in the 5%, talking about the airplane risk, right? It's in the new estimates, many of the new estimates show, including our estimate, that it's really on the top end of this IPCC estimate. And then you can say it's in the range, right? Yeah. Are people well informed? Yes, it's in the range. That's what some say. Yeah, it's in the upper range. So are models wrong? Some are not wrong. All models are wrong. Some are useful, some say. But or everyone should say that. But yeah. So, but it's.
But when do you think the IPCC will start incorporating the 4.8 degree climate sensitivity into their mainstream documents?
It's in the range. That's the point, right? It's in the range. So but I think the range will increase, I think, within the next years. And of course, you have all these maybe if you mention this annual update, I think I think the most recent update did cite our global warming in the pipeline paper, saying, okay, this is one new estimate, which is on the high end. Which is true, for it's on the high end, but it's based on many lines of data, and I think that the next update, I don't know exactly when it will come out. I think in a few months, will probably also show again, cite this number, saying, okay, the James Hansen et al. Showed that global warming has accelerated, and estimate that the forcing increase from decreasing shipping sulfur emissions from global shipping is 0.5 watt per square meter. I do think they will cite that, yes, and with the notation, of course, that this is the highest estimate, the highest recent estimate, at least that's out there.
I just want to quickly mention that the only time we will have enough certainty that the last doubts that the sensitivity isn't on the low end will be after it's too late, right? So if we want to be able to do something about the possibility that it's on the high end, we have to take it very, very seriously right away.
Well, I think you could argue, and I know, because I have actually discussed this with other climate scientists who think it is on the lower end, and they would say whether it's 3 or 4.8, the actions we should be taking right now are the same, and we're not. So, yeah.
Yeah, but that's not true.
Well, what do you mean? I mean, we should be cutting our emissions. We should be taking CO2 out of the atmosphere. We should be.
But adaptation, right? You're right.
Well, the adaptation level will be faster.
If Europe warms by, if the Mediterranean, maybe I can cover it later. Over the Mediterranean, within 3 months, there will be another sulfur emission regulation coming into effect, where again the emissions will be reduced by about 80%. There's of course some uncertainty.
Isn't it already low though? I mean, because you showed that other data for the coastline.
Yeah, but that's
already super low.
Yeah, but the point is that the effect is non-linear.
Right.
That's really crucial, and we've talked about this before. That if you paint something white with even a few micrometers of paint, or I don't know, nanometers even, it will be white. And if you put a thicker layer on, it will be more white. But if you remove 80% of the layer, it will still be white.
Right.
But if you remove again 80% of the layer, then the dark surface below will be much more clear. And I think that's, I haven't seen any study show estimating the potential impacts on reducing sulfur again with 80% over the Mediterranean. But I did see a study which was also published last month with some skeptical scientists as co-authors, showing that the Mediterranean absorbed 1 zeta-joule, which is a joule with 21 zeros, of heat, additional heat in 2024. And that's
Versus
really
what? Versus
in 1 year.
Oh, okay. In 1 year, from
1
2023
zeta-joule, and that's really and that's an enormous amount of heat, accumulating in just 1 year. And of course, there's uncertainties there, but it also the sea surface temperatures reflect that data, right? The sea surface temperatures over the Mediterranean were really off the charts last year, and that contribute, and also in the few years before that. We saw, I think it was in 2 years, 3 years, and I talked about this as well on CNN Turkey. We saw an increase in sea surface temperature over the entire Mediterranean average over 1 year of 0.5 degree. And it takes 3,000 times as much heat to warm water than to heat the same volume of air. So that's really an enormous amount of heat accumulating in the Mediterranean already now. And if this regulation comes into effect, and it will get worse, again, it doesn't matter. I'm responding to your point that it doesn't matter whether it's 3 or 5. It really does matter what happens regionally, right?
Oh yeah. Oh no, the impacts are bigger. I agree. I'm just saying.
No, and then but it doesn't. What you do about it, or what your actions will be very different too, right? If you know that Europe is experiencing an aerosol termination shock already over the past 40 years, because of the reduction in air pollution that happened already over the past 40 years, added 0.2 degrees of Celsius of warming to our summers, which was of course first masked. Then you take, if you are aware of that, you take precautions. You make sure your cities are cooler. You make sure that there's risk plans in effect. There's heat plans. There's the dikes. Our dikes, they could crack if you don't take into account these extreme heat waves, right? And then if you get a strong storm, we could have 30% of our country below the sea. So you really need to take into effect what's happening in the real world. And if someone says it doesn't matter, well, it really does. So please.
Well, I didn't say it doesn't matter. Again, I'm trying to say that
it doesn't matter for the actions steps we need to take, but
the steps to mitigate. The steps to mitigate.
But that's a very limited.
That we're not doing, by the way.
Exactly.
we're not mitigating. We're making it worse by getting rid of the accidental SRM that we're doing, and that's what you've been talking about, right?
Yeah, and I work in Ethiopia, and when I was there, was it I think it's already 10 or 15 years ago when I was first there. I was at this meeting with African representatives of it's called Plan International, which is an NGO working for children, providing livelihood to families. And there was a meeting about climate change, and the international representative from what's called donor countries were all talking about mitigation, right? But the African representatives, they were all talking about adaptation, because they were already experiencing the impact of climate change in their daily lives, and especially also the people they were serving were already very much experiencing the impacts of climate change where they lived, and that's not just from climate change, from things getting warmer, but also from deforestation, from land use change, and of course very much also from the use of biomass for cooking, where they are impacted by the health impacts, but also deforestation causes a decrease. Wood use causes deforestation, which causes cause more soil erosion and cause regional warming because forests keep the region cool. Behind me you see I won a prize. It's called in the Climate Adaptation Business Challenge in 2013 already, where we show that it's really important also to protect forests for climate adaptation regionally. And that's, again, it's not just about mitigation, it's also already, and it was already over 10 years ago, it was already very much also about how can people adapt to the rapidly changing climate as it is. And again, it will change much more rapidly because the climate sensitivity is much higher than many estimated.
Mm-hmm. So we should talk a little bit about what these things that are in the paper, two big ones, and then a bunch of others. Actually, we're planning on having Jim Hansen on Climate Chat very soon. I'm talking to him about like what's a good date for him and everything like that. And so he'll be able to go into some of this in more detail. But the big ones are something that Jim has been working on forever, and I've been working with him on this for, I don't know, 15 years or something, is what's called fee and dividend carbon pricing, putting a price on carbon. Now, there are places that put a price on carbon around the world using something usually in the form of something called cap and trade, where there's you limit the emitters, the big emitters like the power plants and maybe the cement plants, but you don't like go to the source where the fossil fuels are taken out of the ground. You go to the big emitters and say you have to buy permits to emit CO2. And we're going to have an auction every year, and that'll set the price for these permits. Sounds like a good idea, and the policy wonks love it because it theoretically is the most efficient way to distribute this resource and stuff like that. But I think it's BS actually, because it's like the worst possible way to actually do it, because no one knows what the price is going to be next year because there's going to be a new auction, and who knows what the price will be. If there's a recession, the price will just plummet because there'll be less economic activity and therefore less emissions, so no one needs to go out and buy those permits and things like that. So it's a terrible way to do it because no one pays attention to the future price because they don't know what it's going to be. And also, you don't cover the whole economy. You only cover these big emitters. And so anyway, the whole thing is a mess. The way to do it is what Jim calls the fee and dividend. And what you do is you put a rising price on the CO2 content of fossil fuels, and the fossil fuel companies pay it at the well, mine, or port of entry where the fuel comes into the country. So there's very few places you need to charge. So it's very easy to do the accounting for that. And again, it's what comes out of the ground. So it's not like it applies to all fossil fuel use, not just to the big emitters. That's the first thing. Now, of course, and you start off small, you about a $10 per ton, $10 per ton of CO2 equivalent. And that's about 10 cents a gallon, roughly. So it starts off small, but it goes up $10 every single year. So in 10 years, it's at $100, which is $1 a gallon, roughly. And then after that, it's $2 and $3. And some people would argue to make it go up at $15 a year, especially at this point, because these numbers are from like 15 years ago when it would have been a lot easier to address the problem. Okay, but if we did this, the problem would be it would raise the price not only of gasoline, but everything that uses gasoline, the food and everything, airline tickets, everything would go up. And people wouldn't like that. So there's a second part to fee and dividend, and that is that you take 100% of the money collected from the fossil fuel companies, every single penny, and you give it out to every legal resident on an equal basis. And so you and Bill Gates get the same check every month, or same payment, probably electronic payment every month. And Now, it turns out Bill Gates makes a lot more CO2 than you do. Hold on. I'm sorry. And so I'm sorry. So you see, he uses a lot more CO2 than you do. And it turns out that when you do the math, and the Treasury Department did this, 70% of households would make more money on the dividend they're paid every month than they pay in higher prices. And if you're poor, you don't generate a lot of CO2 at all because you're poor. You make the most money. So it's an anti-regressive tax. In other words, it's a tax not that hurts the poor the most, which is what true of any other carbon tax, but it actually helps the poor the most. The rich pay more, but they won't really care very much. There's not going to be a lot for them, and they're wealthy, so they can afford it, and it wouldn't be a big deal. Now, there's a third objection, is that, well, if you put a price on fuel in the United States, that will raise the manufacturers in the United States, their costs, and when they export, then it will be hard for them to sell their products, so they'll be more expensive. So there's a third part to fee and dividend, and that is called a border duty, where you put a border duty on products coming into the United States from countries that don't have their own price on carbon. And they will be at a disadvantage economically selling their products. So they're going to choose to also put a fee on carbon. And that way you get the whole world very quickly to agree to this rather than kind of go through United Nations process. And if the United States, which of course is doing nothing, but China's doing something now, and the EU has been doing this for a while. And if the United States does do something and they all got together for a common border duty, the whole world would have it in a few years. So that's a real way it could be done. It's a carbon tax that people will ask for the price to go up faster because they're making money on the deal. And Canada has this plan already. But what they don't do is when they give you the money, they don't make it very clear it's coming from the carbon tax. It's really important that you give a separate payment and you label it as the carbon tax dividend, and you really make a big deal of that so that the public gets in their head that this money is coming from the carbon tax. So even though Canada is doing the general concept, they're not really executing it well in terms of publicizing the fact of what's really going on. So the public doesn't understand that this money they're getting comes from that. So there's ways of doing it right and there's ways of doing it wrong, and I have a TEDx talk on this, and I have a white paper I wrote with Jim Hansen on this that we submitted to Congress, and I will later put these links in the description. They're not there right now, but I can put it in after the show ends. So that's one of the main things he pushes for, and the other main thing he pushes for is research, not deployment, but research on solar radiation management, or SRM. Jim thinks that the Earth energy imbalance, this million Hiroshima atomic bombs per day, is too high right now and should be reduced. And he also knows that even if we lower our emissions, it will take us decades to do that. And we already have 2.5 trillion tons of CO2 that we've already emitted. And about half of that stays in the atmosphere, and that half lasts in the atmosphere for hundreds of thousands of years. So things don't get better when you stop emitting CO2. It just hopefully stops getting worse, and it still could get worse too. And so he says it's really important to study that because he sees there's resistance to even talking about SRM. And there's groups that say we shouldn't even research it. It's such a terrible thing to do. And of course, as he points out, if you want to look at the risks of SRM, you definitely should. But you have to look at the risks of doing SRM against the risks of not doing that. And we just did a show on this with David Keith a few weeks ago, where a new paper shows that not doing SRM will kill like 400,000 more people a year than doing SRM. And that was very conservative, by the way. It only assumes certain kinds of things. It doesn't assume all the damage, like it doesn't assume a famine could happen from climate change, for example. So he's just saying, yeah, I'm not saying that it's risk-free. It's just that we have to balance the risks at this point. And he also, when asked, isn't that called solar geoengineering? He says, no, it's the purpose of SRM is to reduce the geoengineering that we've already been doing to the Earth with the emission of 2.5 trillion tons of CO2 and methane and all these other things, and aerosols, et cetera. So that's in a nutshell what Jim is calling for. He did have some hopeful words for young people, but I'm going to, rather than talk about that here, we'll wait for Jim to be on the show and have him give his words to us directly. And Leon, any thoughts on the SRM or fee and dividend parts of the paper?
Yeah, I'm not an expert on the subject. I know we had, I think it's already about 10 years ago, we had Jim in the Netherlands talking about this as well to students. Yeah, what I would really love to see is someone who is maybe an economist, explain how, like, what are the best ways to implement it. And I think I'm sure it's almost impossible to do it globally, but I think that's because of course Jim is a great climate scientist and a great physicist, and but he cannot explain it to me very well how, like, what are the economic implications and benefits. I think you explained it already quite well, where you show, okay, most people will benefit from it, but if you have an economist who does this every day, and they know all the words, they know all the implications and all the benefits, and they can, so I would love to.
Well, there is a report published long ago from a group called REMI, Regional Economic Models Inc. And this was done on behalf of Citizens Climate Lobby. We can cover this next week, by the way. And they did it for the United States. They focused on the United States and showed that it would create, boy, I used to have the numbers, increase GDP by 1.4 trillion, create millions of jobs. I can't remember the exact numbers anymore. It's in my TEDx talk, so you'll see them there. But so there is the economic backup, and actually it's the Treasury Department.
Yeah, but that's what many people want to hear, right?
And also my thing I wrote with Jim actually has some references and stuff like that. So it's a kind of a summary for the Congress, but you'll find information there. Again, I'll put that after the show ends. I'll add those links to the description. And next week, so everyone, by the way, listen next week. We'll talk about not just fee and dividend, but the other work that CCL is expanding into and what they're going to be doing now that Trump is president, and dismantling climate research in the United States and scrubbing the words climate change from websites. It reminds me of a quote from Neil deGrasse Tyson, who said, "The good thing about science is that it's true whether you believe it or not." And that's about what we're all going to find out. It really doesn't matter if you scrub climate change from websites. It doesn't change climate change one little bit.
I wish it was the other way around. I wish if we would just not believe in it,
and it goes away.
Of course, that's denial, and you talked about it before about what denial means. I think we don't want it to be true, and I understand that very well, that people don't want things to be true, but it doesn't change the reality. But I wish it would. It would be nice.
I think it's a good time for questions. So Stacy,
maybe Stacy can go first. But I also had some questions I asked people before to.
All right. Well, let Stacy ask a couple, and then you can go through your list. You asked on Twitter or Blue Sky, right?
Exactly.
Yeah. Stacy, are you there? And if not, we can maybe go with the ones you have. Let's see. Stacy.
I can start.
All right. So go ahead. Go ahead.
So I have it here. Let me start with this one. Share. Let me tell me where you see.
Yeah, now I can see it.
Yeah. So Ryan Katz-Rosine asked me to provide some details on this point, where Jim said, where this from the paper, the recent acceleration of the global warming rate, so the global warming acceleration should not last long. That acceleration is driven mainly by a unique forcing of about half a watt per square meter caused by reducing sulfur emissions from global shipping.
Mhm.
And yeah, in a way, I do agree with that it's one forcing, right? It's just it's not every year or every 4
Step
or 5
change.
years where we reduce sulfur emissions by this much globally over the oceans. So with that, I agree. But again, as I mentioned before, so I think this was a jump, and the increase in warming, it will take a while, and I'm not entirely sure if, and I'm sure Jim would say the same, how long this will take, because
Well, I think he said in the paper, he said a third of it
Yeah,
happens in the first
course,
10
but
years. The
yeah,
second
he
third
did.
happens in the next 100 years, and the last third happens over the next 1,000 years. So we're going
Yes,
to see the most
but
of it now, and then it's going to
but
taper off.
but how long this acceleration, because that's the question raised here, how long this acceleration will last? And I think that what I mean with Jim will agree, because I think the model, I'm not entirely sure, but I haven't checked, but I think the model, where at least what we did in global warming in the pipeline, was use we showed the climate sensitivity model, and then showed what how long it will take for this warming to come into effect, and that's based on a doubling of CO2 scenario, right? But this forcing is not a half a watt increase in global greenhouse gas forcings. That's not what happened here. This forcing is a half a watt, or whatever number it is, decrease the globally average forcing but centered over the oceans, and the oceans accumulate 90% of the heat, and a forcing change of changing in how much sunlight is absorbed is very different from having a global average, nicely homogeneous CO2 forcing increase.
Mhm.
So I think that's an important disclaimer here, that we don't know, right? We don't know yet exactly what will happen here, and that's one part of the answer. So we shouldn't, as George also shows you, we shouldn't underestimate it. We shouldn't underestimate the forcing, especially over the oceans, of the cloud feedback, because
By the way, I want to make it clear. The shipping reduction in pollution, that ship pollution helps create clouds. Separately from that, not that effect, but there's a separate effect. When we had George Saludius on a few weeks ago, talked that the data shows that just global warming, the planet getting warmer, is that itself is decreasing cloud cover over critical regions of the Earth, and is part of the reason why the doubling of CO2 sensitivity is closer to 4.8 than 3, is because
Yes.
before that we didn't know whether changes in clouds would cool the Earth more or heat up the Earth more. And now the data is coming in, and of course we always have this optimism bias. Well, maybe it'll work out in our favor. Well, the answer is no. It didn't work out in our favor, and the loss of clouds due to the warming Earth is a contributing factor to warming. I
Yes,
should say that
and
besides,
that point, the point is warming, indeed, greenhouse gas warming causes indeed what George estimated, and that's already before 2020, right? Before this global regulation came into effect.
Mhm.
There was an decrease in cloud cover, as this new study also shows, where George is also a co-author of, that a big part of this increase in how much sunlight is absorbed by our planet is from cloud feedbacks, as I highlighted at the start of our conversation. But that cloud feedback will also happen from this forcing change of shipping emission reductions, right? Because that's also causes warming. So if you reduce shipping emissions, there's less sunlight reflected back to space. That causes warming, and the warming causes the oceans to warm more and more and more, and that causes also the atmosphere to warm, and that reduces cloud cover, and that increases the absorbed solar radiation, and that's again the cloud feedback, which, as George very clearly explained in your conversation, is much stronger than most thought, which leads to this higher climate sensitivity, which means the IPCC best estimate at least was very wrong, and so maybe we can say they were 5% right, because it was the 95% range, so they were 2.5%. So the highest, so like, because you have a 95% range, the top, if you have the top value, that's like the top 2.5%, right? Because the bottom is also 2.5%. So it's yeah. So and then
Okay.
I think that, and now I just want to elaborate further on the answer I just gave about whether acceleration will stop now, which is globally, like let's assume I really don't like to assume that it's the same as global CO2 forcing, where you have much of the effect in the first 4 years, but let's assume for now, and then even if that is true, right, then we still have a lot of other desulfurization in the pipeline, and that causes warming in the pipeline, right? And that doesn't mean that CO2 emissions will decrease as well because coal-fired plants will decrease. No, that is because coal-fired power plants are regulated, and now showing India, to stop emitting sulfur, to stop polluting the atmosphere over India here. And then you already see that there's an increase. This is in units, but you can also show that in megawatts of installed capacity, where you see that about 20 gigawatts, 20,000 megawatts worth of coal plants have installed in India desulfurization systems, but many more. That's like, what is that? That's 1,000 gigawatts. It's mind-boggling. Gigawatts of coal-fired power plants have their contracts awarded. I think is that true? At least 238 units. I think they missed a zero there, but I could share it later. Where they have 238 coal-fired power plants are regulated to install, or they have the contract awarded to start desulfurizing, and that will cause a lot of additional warming, not on top of what we already see. But this warming will very much be centered over India, which is, of course, a country with the highest population in the world, with I think 1.4, almost 1.5 billion people living there, and with a lot of other countries in the region, like Bangladesh and Pakistan, with very high population densities, which could be very much impacted by this. Because, for example, during COVID, there was a regional increase in sunlight reaching the surface of India, especially over the North India, of 16 watts per square meter. 1.6. So that's really, over the ocean, North Pacific, absorbing more sunlight is worrying. But if that really happens where people live and grow their food, I think that will be very worrying too. And then, as I already mentioned, the Mediterranean, you see this desulfurization, the scrubbers. Mediterranean will also desulfurize further this year.
So it's not just, the answer is not just ships. All over the world, we're cleaning up air pollution which, by the way, this air pollution helps contribute to the deaths of 8 million people a year. This is not a safe thing. It's a terrible thing. It's one out of 5 deaths on Earth are caused by fossil fuel pollution. So it's good that we clean it up, but there's consequences for cleaning it up, and that is more climate change, more global warming. I think we have Stacy back now. She had a little glitch there before. So Stacy, welcome to Climate Chat, and let us know some of the questions that are coming in from YouTube.
So sorry about that. I don't know what happened. My Zoom totally quit. And I have so many good questions. The one comment I wanted to make in the paper, something that was missed and something that has been a sidebar on the YouTube chat is no, I mean, obviously, transportation is my first and foremost, and that is the largest contributor to greenhouse gas and just all bad things, you know. But
Ships are also transportation.
What's that?
Ships are also transportation.
Yes. Oh, no. He does address that. Sorry. The thing he doesn't address is about animal agriculture. In fact, the words animal and agriculture are included a total of 3 times in the document. And I myself am a flexitarian. I've been one for, I guess, 9 years now. I haven't given up dairy and eggs yet, but it's one of those things where I know I should. And if everyone would start stepping away from the things, from back off the fossil fuels, back off the animal ag, we'd be a lot better for it, especially those of us who have options. I mean, the ones that are, lab-based stuff is it's so good, it's better than the real thing. It's safer. Like, I mean, I'm wishing for more avian flu or something, because we need to really cut that down. Anyway, that's my soapbox. I want to get to some of these questions because they're so good.
Go for it.
At what point of fossil fuel utilization can we say that near-term human extinction is most likely inevitable? Can we calculate that?
I don't think it's covered in the paper, by the way. I don't think that's something. Yeah.
No,
I think we're quite a species that can.
It's not really a good question, I think, because what does it mean? Extinction means every last human on Earth is gone. I mean, humans can survive really well, especially if you have enough money and your bunkers or whatever the hell you're going to do, and then after you kill everyone else off, you're still surviving.
How do you measure that?
Yeah, how do you measure it, right? NASA satellites.
True.
So that, if we're going to lead to billions of deaths and collapse of civilization, to me, that's kind of the measure.
Yeah.
The extinction question is an interesting one, I guess. But if we're going to have literal countries collapsing because of lack of water, too much water, fires, floods. By the way, an AMOC collapse, forget extinction. An AMOC collapse just screws up everything. It just changes. It doesn't even necessarily make where you live worse off. It might be better in some ways, but your agriculture isn't set for that. Your cities isn't set for that. They're certainly not set for 10 feet of sea level rise if you're on the coast, and all these other things that are going to happen. So I think it's like bad enough with what's going to happen this century than to peg it. Well, the only thing that really matters is extinction. By the way, and then extinction happening to many, many species right now at 1,000 times the background rate. So if you really care about extinction, you care about that.
I think that was a point I wanted to make as well. That, and even I think today, or at least this week, there was a paper published in ESD, and then which shows that the warm water coral reefs, the tipping point for warm water coral reefs, is 1.2 degrees Celsius warming above pre-industrial. For the long term. So if you keep that warm, the temperature rate,
we're past.
We're already above that, exactly. So, and that's long term. So the warm water coral reefs cannot survive the warming we have already caused. Maybe some will survive, but this is already causing a widespread. This will already cause and is already causing widespread extinction of warm water coral reefs around the world, as we saw last years, when most of the coral reefs were seeing coral bleaching, seeing heat waves, which were off the charts, where they had to update the charts to make it fit. So that was already happening in the current warming, which indeed is above 1.2, and they show the CO2 concentration of 350 parts per million as the threshold. And we are now at 420 or above 420 parts per million for CO2. And as I mentioned, for all greenhouse gas combined, we're at 560 parts per million. So that's, I think the answer is, you know, human extinction is bad, but this is it's already very bad. So yeah.
Just want to quickly mention, if you lose coral reefs, 40% of the animal life in the ocean depends on the bioproductivity of coral reefs. So it's not just pretty vacation destinations.
Exactly. That's also what this new study mentions very clearly already in the abstract, is that hundreds of millions of people depend for their livelihoods, for their lives, in different ways, of course, on these coral reefs. So it's really, they are a crucial part of the global ocean ecosystem. And I think that's really also important because global warming is, as I mentioned, very much ocean warming. And the oceans, they harbor so much life, right? And many of the fish, their metabolism really increases a lot when the temperature increases, because they are cold-blooded, and the biggest animals ever to live on this planet, the blue whale, now live in the ocean, right? They are dependent on the current climate, and if we change it as fast as we are changing it now, there's no adaptation to it. There's no survival of the fittest with this rate of change.
Okay, what's the next question?
I have two about climate scientists. What is really at stake between the scientists tied to a linear model of warming versus those who describe acceleration? Do you think it's political, sociological, psychological, scientific, anything else?
Well, I'll say this quote that I like is that climate scientists are conservative in the opposite way that a risk manager is conservative. And we just did a show on the University of Exeter faculty of actuaries, which are insurance people, do calculations for insurance companies, who are looking at risk from a risk manager's point of view, where a 5% risk of catastrophe is totally unacceptable. Whereas, you know, the climate scientists, well, it's only like a 30% chance that it's going to really not work out. That sounds pretty good. So there's a lot of psychology behind it. Jim Hansen wrote about this many years ago, I think 2008, in a paper titled Scientific Reticence, where he talked about, I mean, here's some basics. If you're an academic and you're publishing papers, you have two things that could happen. One, well, hopefully what you write about turns out to be correct in the future. But if it's going to be wrong, let's say you would much rather not publish a paper that turns out to be right than to publish a paper that turns out to be wrong. The first thing doesn't affect your reputation. You just didn't publish a paper. Well, maybe you need to publish more on other subjects. But if you publish a paper and it turns out to be wrong, then that really hurts you. So what you want to do is you only publish a paper when you're 95% sure that you're correct. This is 2 sigma. And so when it comes to sea level rise, what you hear from scientists is that it's going to be at least 3 feet. Well, no, it's going to be 3 feet. They're right in the sense that it's going to be at least 3 feet. But the fact that there's a really high probability it could be 6 feet, or as Hansen says, 10 feet, you know, they don't want to publish that because they're not 95% sure of it. They're 95% sure of the 3 feet. Now, this is fine if you're talking about black holes or dark matter or something like that. But when you're talking about survival of civilization, it's not a good idea to go with it. And to think about it in other ways is also the military. The military would never accept, I mean, they would always cover their ass for any.
The question is not about science.
Go ahead.
I think the question is not about science.
It's about psychology. Yeah.
Because the question was about linear or non-linear. And the science, even by those who are even sometimes ridiculing or comparing James Hansen to climate deniers by saying it's like the pause and the right. saying he's exaggerating. Those same scientists are showing acceleration in their own research. So it's about communication. They are communicating one thing while their science shows something else. And yeah, some would call that lying.
Or they say the ones
No,
we've
but,
had on.
And I think that's also what this shows, like aversion to the wrong kind of error in climate risk communication. Right? It's about communication because the science says one thing, but some science say to communicate also publicly that it's not that bad. It's not that bad as the science shows, right? For professional risk managers, they have a high tolerance in being wrong, but a low tolerance in that it's worse than they expect, right? And I think that's also a question. Like I think I got from Thomas here is if one is like is James Hansen a conservative? That's a bit of a wordplay, of course. I think that's quite a nice way to say that he's wants to conserve the future of our children. But and the other question is, where are we now? And I think we are at where we are at point A, where we can be stewards of the earth. I think that's what Hansen proposes in this paper, where we try, for example, through indeed in putting a carbon price there, but also funding nuclear power plants and development of the nuclear safe nuclear power, because that could, of course, provide us with the energy we need. That's an important part of the paper as well, that we use a lot of energy. We need a lot of energy, and we better get that from sustainable energy sources, which nuclear power, as the IPCC report itself shows, is low, very safe if done right, and it has of course very low footprint, both from CO2 emissions and in land use and many other things. So he proposes to become stewards and also research SRM. So if we need it, or if people do it, intentional sunlight reflection methods, that is done right. So we do need the research. And then, so I think that's a good way, that we need to become stewards of our planet. That's really.
But right now we're on B. I mean, that's we're not stewarding, we're not reducing emissions. We're not doing SRM. We're not doing carbon removal at scale. We're not doing any of those things. We're just continuing business.
Yeah, maybe C. That's.
Well, we're not at C yet. C is when the Earth itself takes over from us.
Yeah, but
and the feedbacks exceed what we do. Yeah.
For the coral reefs, maybe we are, right? And
in the West Antarctic ice sheet, as Jim pointed out, we might have already passed that threshold already. Yeah.
And that was also a question I've seen somewhere else. Is like talking about tipping points, and this is of course also what I just showed that, and what Jim also mentioned in the paper and in the press talk is what are points where, for example, the AMOX, when the AMOX shuts down, points of no return. So there's a tipping point, but also that we cannot go back. Like
right.
The example, if you are in the canoe, and if the canoe tips, it's much harder to get the
back
canoe
in,
especially if you're in the middle of the ocean, right? To get it floating again. And I think maybe with the AMOC, for people, it's often hard to imagine. Okay, maybe you can start it up again, or if it's not too much, slow down too much. But for example, if the ice has melted, you can imagine in a warmer world that it will be very hard to freeze it again and to get this to lower sea levels again, right? Or if an ecosystem, if the species in the oceans, if coral reefs or other species are dead and extinct, it will be almost impossible to get them back. And if the Amazon is gone, it will be very hard to rebuild the Amazon, because it also the
self-sustaining.
Yeah. They are self-sustaining, but then if they become, if you take away the forest by deforestation, but also by by creating a climate where these forests cannot survive, or by changing rain patterns, either by increasing or by decreasing aerosols, right? That's also the reason why we need SRM research, because we don't want to do it wrong and just kill the Amazon rainforest by changing the climate in the wrong way.
Sure.
Because we already changed the climate, whether we like it or not. I think that's also important.
The status quo is no longer an option, as I like to say. I mean, people think they look at SRM and say that'll make things worse. Well, versus what? You know, it's not. You don't get to have it the way it used to be anymore. So you got to choose your poison, I guess. Let's go through the questions kind of quickly because we're way over time.
One is a sort of fact one, and I know we've covered it in the past, but it bears repeating. Why do so many climate scientists say warming will stop almost immediately if we get to theoretical net zero? Won't it take a while for the energy imbalance to get to zero?
So the quick answer for that is, if we're lucky, and not assuming ECS is really 4.8, but let's say it's 3, that's what the IPCC and these scientists assume, it is true that there is warming in the pipeline, and that will cause the Earth to continue to warm. However, that is counteracted by the fact that the oceans will continue to take up CO2 even after we stop emitting, because the oceans don't know how much emissions we make per year. It's not measuring that. It only knows what the total is, and the total is out of balance. So even once we stop, the oceans will continue to, and plants and soils will continue to take up CO2. So that will lower CO2 in the atmosphere once we stop emitting, and that will sort of, if we're lucky, counter that. There's 2 more things. One is, as we cut emissions, we're going to cut also all the aerosols from burning fossil fuels, and that will make temperatures go up. But counter to that is, we're also assuming we're not going to emit any more methane. Methane is extremely powerful greenhouse gas, 120 times as powerful as CO2 while it's in the atmosphere. But the good news is it only lasts for about 15 years in the atmosphere before it's destroyed and turned into actually CO2. But you got to remember, we've gone up by 120 parts per million since the Industrial Revolution. 140 parts per million. We've gone up 1 part per million in methane since the Industrial Revolution. But that 1 part is like 2/3 of the warming of the CO2. So it's a very powerful greenhouse gas, and it will fade away if we're lucky and we don't have feedbacks from Arctic and permafrost and stuff like that, if we catch it in time. And so when you add up those 2 positives with the 2 negatives, it's supposed to all cancel out. And again, that's if we're lucky.
Yeah, I show here the carbon cycle feedback. So land carbon response to CO2, and the ocean carbon response. That's so the ocean. If you increase the amount of CO2 in the atmosphere, then the land will absorb more CO2, which is the carbon, the fertilization feedback is called, because of course CO2 is plant food, which doesn't mean it's not a greenhouse gas, of course, but it is plant food. And the oceans, if you increase the amount of CO2 in the atmosphere, the oceans will take up more of the CO2. So that's often also in a way confusing, because I showed you the feedbacks in the climate system, which are the radiated feedbacks, if you would keep greenhouse gas concentrations at the level they are today. Right? That's what I was highlighting at the start of our conversation. But all the other feedbacks are also important. Of course, that is only in that hypothetical scenario of stopping the CO2 emissions in the atmosphere, or stopping to emit CO2. But we are not doing that. So I think that's also often a discussion about the energy imbalance. I think that's the question here is maybe it's also about understanding the definition, right? What does energy imbalance mean? That there's an imbalance in how much warming we get, and then some respond to that, yes, but there's also an imbalance in CO2, right? Or in how much ocean and land can absorb CO2. But that's only in a hypothetical scenario. We're not talking about the hypothetical scenario. Of course, that's a question here. But we are when James Hansen in his paper writes about Earth energy imbalance, he's not talking about the hypothetical scenario where we instantly reduce emissions to zero, also known as the instant human extinction scenario. We are talking about what will happen in the next decade, the warming in the pipeline in the real world, where we continue to use energy, where we continue to grow rice and try to grow food in different places, and also many would like to still indeed consume animal proteins. I understand we need to reduce that, but that is the reality we have now, we are dealing with now. And that's the real energy imbalance we are talking about, not a hypothetical net zero scenario.
Although I'm actually interested, though, even in the theoretical discussion of the instant human extinction, as you put it, if ECS is really 4.8 instead of 3, and yeah, I don't know, the ocean uptake, I think that's kind of well known, right? I mean, I don't think that's going to change much. There is a question, though, by the way, the plants, even though they grow more with CO2, as it gets hotter, their vapor pressure deficit goes up, and that stops them from growing. And we did a whole show on how vapor pressure deficit has stopped the Earth from greening for the last 20 years. So there's some of those things. But basically, I don't know, like, what if Michael Mann accepted 4.8 instead of 3? Would that change the view that the Earth stops warming when we stop emitting?
Yeah, you would have to ask him what he thinks about that. But indeed, I just showed another paper that was published this week. One of the co-authors, Vincent Gauci, read a really great article. I recommend everyone to read it, which is really accessible, where they show that the reduction in air pollution could increase methane emissions from wetlands.
Sure.
And I think that's a lot of research like this has been coming out. Decrease in air pollution could cause an increase in boreal forest fires. Decrease in air pollution is accelerating warming. Decrease in air pollution increases the extreme heat waves where people live. Reduction in air pollution increases methane from wetlands, right?
And how about permafrost melt and
exactly. So
cloth rates?
Time out, Leon. The other side is going to pick this up and say, "Hey, we should not decrease air pollution." Sorry.
By the way, it's important to note that this is accidental solar radiation management that we're doing, which kills 8 million people a year. By the way, no one even mentions a word that burning fossil fuels kill 8 million people a year. They're so worried about the few people that might be killed by some way of addressing climate change, right? That's a trolley problem.
13 states have passed. You can't do solar radiation, or you can't intentionally geoengineer. So
but doing it on purpose is 1,000 times safer from a pollution point of view, because first of all, you need a lot less in the stratosphere because it lasts for a year instead of a week. You need a lot less. It also is spread out mostly over the ocean, 2/3 ocean, so you're not going to breathe it in anyway. And it tends to rain out instead of coming down as particles that you breathe in. So David Keith said, because those 3 reasons put together, it's actually literally 1,000 times safer. So instead of 8 million people, it would be 800,000 people, whatever to the math.
And I think that's the point. Sulfur is not a bad thing by definition, right? It's part of nature, and of course we add more to it, but we also add a lot of other things to nature, right? Sulfur is also part of fertilizers. Plants need sulfur, especially onions, for example. The decrease in sulfur emissions over the United Kingdom has led to a decrease in onion growth and a decrease in taste from onions and a decrease in tears rolling down people's faces when they are cutting onions, because there's less sulfuric acid created in their eyes but when they cut them, right? So there's, if
less
you understand
crying.
sorry?
less crying due to
That's right. That
reduction
might be,
in ship pollution. Wow, that's one I
No
didn't
more
thought
tears.
of.
and
Wow.
that's you need to understand if you and I think that's really interesting by from this new study. And I want to talk with one of the co-authors as well on this and have a climate chat about that. Is to talk about this study and what we can learn from it. For example, can we use that the knowledge that decreasing sulfur emissions causes more sulfur methane emissions from wetlands? Can we use that knowledge, for example, to improve to reduce methane emissions from rice fields, which are also in wetlands, right? So you can use the knowledge from science to improve the world. I think that's really a crucial message here, right? It's not doom and gloom. I think I've heard more people say that, like, oh wait, you can cool the planet intentionally, so maybe we're not doomed. So the biggest doomers maybe become a bit positive by understanding the science better, right? And it doesn't mean that we have to do it, but we have been doing it on purpose. So we need to learn how to do it right. We need
Let's
to
try to end this in 5 minutes here to keep it
Okay.
2.5 hours. But
Actually,
let's see if Eli has a question first before
sure. Go
go
ahead.
to any others. Eli, are
Well,
you there? Any
so
questions?
yeah, thanks. So
Quick
first,
one?
I'd just like to comment that there was the webinar that was mentioned earlier that Hansen did a few days ago. I put the link to that.
I'll put it in
chat.
the video description after the show.
Highly recommend it. It's also a master class in climate communication. And it really lays it out clearly, like the intent of the paper was very, very clear and persuasive. So regarding things we've discussed, I was just wondering, and this is the thing that I always bring up, or the things that I always bring up, the uncertainty in the amplifying feedbacks and the tail risks, and people don't talk about this as much because we're doing such a terrible job about facing the modal risks, and this is precisely what Jim Hansen said that he was on, so he didn't really engage on tail risks at the time, but I'm wondering what you see as the revised picture of tail risks.
Well, I think they're always pretty high. I mean, collapse. I mean, in the paper, it talks about, West Antarctic ice sheet collapse and AMOC collapse and 10 feet of sea level rise by the end of roughly the end of the century, 50 to 150 years. And that doesn't include all the other tipping points and the Amazon and the monsoons and on and on and on. The bad stuff is pretty bad. You don't need extinction to think it's going to be. I mean, it's basically, and by the way, we're only talking about 2 degrees here, but we're really on path for 3 degrees by the end of the century and 4 beyond that. And I still memorized what Kevin Anderson said about 4 degrees. At 1, it's not compatible with an organized global community, is beyond adaptation, devastating to the majority of ecosystems, beyond adaptation, and would lead to higher temperatures because 4 would lead to 5 and 5 would lead to 6. So you just don't want to go there. I mean, it's really, really bad. But
so
what we did talk about today a little bit of how we can take steps to not go there, but we're so far choosing not to. By the way, we are, as also Kevin Anderson said, we are choosing to fail. We're not failing because we don't know what to do or what's going on. We know exactly what's going on and we know exactly what to do. We're just choosing to fail. We just don't care about the future at all. We only care about short-term stuff. And also, we have so much disinformation out there that people could vote for someone who actually says climate change is a hoax, even though that's going to hurt all their children. But they don't know that because they're fed BS. So there's a lot of issues there. We're going to try to keep talking about them on Climate Chat going forward. But I think we should call it quits
So
now here, unless
just
there's anything.
I'd like to add, there's one really good closer question.
Okay, what's a good closer question?
Leon does a wonderful job explaining the science, but I'd love to hear his opinion on what he believes our odds are to meaningfully address the threat of climate change.
The odds. Well, I think when we start to realize, or where we are more or less realizing it, the few people who listen to this already realize, at least more than most others, how bad it really is. But I think once we start more people start realizing how bad it is. For example, what I mentioned over the Mediterranean, when we do need some disasters, unfortunately, for people to start waking up. But I do believe that humanity as a whole is quite flexible and can really put a lot of work into making things much better than they would be without doing that, right? If we love our children, we love our families, we love our country, and we want the best for all of it. And I think most people also love that planet. And once we start realizing that, once people really start to realize what we're doing to the planet and what we impact, I think it is possible for people to start cooperating again and to work on a better future.
So that's great. That's great. And I kind of agree with that. I mean, I do think it's going to take some more disasters. I do think that that's why I guarantee we're going to do SRM, because when we finally decide to do something, that is the only thing that will actually have an impact very quickly. Deciding to lower our emissions to zero will take decades, and then a few more decades before you notice we did it. And same thing for carbon removal. You're talking about decades and decades before the impacts show up in the climate. Whereas SRM, as we just saw, it happens in a year or so. So
we will definitely do it, and that's the point also Jim is making in the paper, that
he doesn't say exactly that. He steps back just a tiny bit.
He says
study it.
People will demand it. I think that's what.
Oh yeah.
I don't have the full sentence. It's not, and that's the point. It's an advice to do the research, because people will demand it when they realize the impacts, the risk of not doing it will far outweigh the risk of doing it.
Sure, because it seems obvious, by the way.
Yeah, it is.
That's, by the way, why the people say you shouldn't do research.
And it's extremely cheap, of course, right? And the easiest way, and I think that's something many ask me about, like, should we put the sulfur back in the shipping fuel or shut off scrubbers? I think that will be proposed more and more. And it will become more and more clear, I think, that depending on where you do it, either using sulfur or using other particles like sea salt, will far outweigh the benefits of not doing it. Of course, you have to take into account the health impacts and the environmental impacts, etc. Sure. And it's relatively very cheap, and the technology is partially already there. So indeed, people will demand it, and we better make sure that when people demand it, it will be done as safe as possible, with reducing risks instead of increasing risks.
It's all obvious. It's just extremely inconvenient.
Well, I do think that the fact that people will demand it, I think the people who oppose SRM and say you shouldn't do research, I think they know that. They feel that it will be demanded, so they want to head it off at the pass and say, don't even look at it, don't even talk about it, which they can't do, of course. But anyway, so that's we'll continue to be talking about SRM and AMOC on the show. We also do have a special announcement about climate chat and where it's going and Leon and things. But let's leave that for a separate little thing, because this is the end of a 2.5-hour thing. So I don't think many people would see it there. We'll maybe do a short little something and talk about that sometime, maybe later this week. And again, next week with Citizens Climate Lobby. And we have, Jim Hansen is trying to schedule that in soon. It could be next week. It could be the week after. I don't know yet. But we'll let you know about that. So please follow us on Blue Sky and on Twitter. And please like this and follow and hit the little bell too, so you get notified of upcoming episodes. More people that follow the channel, the more other people that see it. So it's a little bit you can do to help climate is to promote this kind of content on YouTube rather than just cats and things like that. The cats are fine. Um, anyway, so thanks, Leon, for spending time and helping us understand this really groundbreaking paper. It's really important paper. Hasn't gotten as much information as the press as it should have. I'm going to put a lot more information in the description in the next 5 or 10 minutes. And so you'll have references to that, everyone. And thank you for being here. Thanks, Stacy. Thanks, Eli. Thanks, everyone, for joining us. And we will see you next time. Right. Bye-bye.